All right, so we're here today with the lecture material on 2.1.4 and 2.1.5, which are going to be types of plate boundaries and evidence of plate tectonics. So let's go ahead and get started on that. So 2.1.4 are the types of plate boundaries. So we need to really pay attention to this in terms of the three different types of plate boundaries. We've got plates that move away from each other. Those are going to be called divergent. They're also known as constructive boundaries because where they diverge, new mantle comes up in this form. We've got those going towards each other. So the opposite of divergent is to converge. So that's going to be convergent plates where one will subduct underneath another. And those will be called destructive because one is being destroyed as it moves back down into the mantle. And then ones that slide alongside each other. Those are called conservative because they don't neither create nor destroy or transform boundaries. I'll usually probably refer to these as divergent, convergent, and transform. So these three actions of plate tectonics have different results on Earth, and we've really shaped what the Earth's features have and what Earth's become today. You'll see some rock terms in here, which you can click on and find a definition yourself. However, we're going to have a whole section on that in 2.1.6. So what happens at the divergent boundaries? Basically what happens, remember, to diverge means literally to go away from one another. So divergent plates do exactly that. They're also considered to be constructive, like I said, because where the two plates spread apart, new mantle comes up and becomes part of the crust. So it is creating new crust, therefore it is said to be constructive. And then when it's in the ocean, when this happens in the ocean, in which most of the time a divergent is in the ocean, what this is called is seafloor spreading because the seafloor is spreading apart. What happens is new magma from the mantle rises to the surface to fill that gap that is filled. So there's really not really a hole in there. There's probably a depression, but what it is just new mantle moving up. This is runny lava, which pours out almost continuously in a non-violent way and cools to form basalt. So these are like volcanoes technically because magma is coming up out to the surface, but they're like very, very steep, non-steep, gentle sloped volcanoes basically going on there. This forms basalt. What happens as a result of this action are rift valleys. If this does happen on the crust, when this happens on the crust, splitting two plates moving apart is known as a rift valley. So if the East African rift actually happens on land, so that's a cool one. In the ocean, rift valleys result in what we call oceanic ridges, and these are really cool. They're underwater mountains. There's an example here. These examples are really cool if you click on them. So that's the Mid-Atlantic Ridge. And volcanoes and earthquakes can result from divergent plate boundaries, but however, since it's just a gentle motion moving up, these aren't usually your strong earthquakes or explosive volcanoes. They usually require, in order for it to be explosive or a strong earthquake, would require more friction than what you're getting here. This graphic shows the formation of a continental rift valley. So as you can see here, we've got the magma moving up, spreading apart, and this is a place where continental crust is spreading apart. All right, you can see what's happening here are these plates are moving away from each other. That's the first part. The magma is going up, causing some upwarping. That's what it's called here. You see the volcanoes here. Basically, what happens there is that as it spreads apart and that upwarping happens, it will start to concave, and that will make your rift valley. All right, so a valley right in the middle of that divergent plate boundary. You'll end up getting a linear sea in here. So this is basically filled in with water once you have that depression, but you still have that magma coming up, and that magma is still making new crust. It's just now it's underneath the water. And then finally, let me get rid of all that. Finally, what happens is that you have the mid-oceanic ridge, which is your basically line of mountains. In the middle is going to be a rift, which is where the new magma is continuously being spread. So these are your underwater mountain ranges, are usually found from these divergent plate boundaries. All right. I should have a cool animation here. Hopefully it plays on this window. It does. Good. All right. Maybe the link is broken. We'll get to it in class if we can't see it there. All right. So convergent boundaries. Convergent boundaries are where you have two plates. They're moving together and one subducts underneath the other one. So to converge literally means to come together, so convergent plates do that. They're also considered destructive because the heavier plate, the more dense plate, is going to subduct underneath the Earth. They usually occur at oceanic continental plate boundaries. One plate, usually the oceanic, that's important to remember, the oceanic plate, right, is going to be more dense because it's got a lot of water sitting on it, compacting it down, compacting it down, compacting it down. So because it's more dense, it's the one that will sink underneath the continental plate, all right? So what happens there is called a subduction zone, all right? Where it goes under is called a subduction zone, and we can see that right here, all right? We've got the more dense oceanic crust right here. And what's going to happen is that it's going to, as they move together, that's the plate movement, as they move together, because this guy's heavier, because all the water on top of it, it's going to go underneath the continental crust. And then what's going to happen here is just like what we saw at the divergent plate boundary, you end up getting a depression right here, which is called a trench. All right, so you'll have an oceanic trench, like a deep part right on the coast. All right, and what you'll see here, though, is because of all this friction, there's a lot of friction right here, and it's going to actually melt a lot of the lithosphere, and that will start to rise up. And as it rises up, that magma is actually being forced up by this frictional motion of the lithosphere going down, and that can form mountains and volcanoes. And specifically, these are where your explosive volcanoes are, because this is a lot of friction that's providing a lot of energy, and you're going to get a lot of earthquakes here as well. So these are your most destructive in terms of natural hazard plate boundary movements. So sediments, back up to below where we did subduction zone. Sediments on the sea bed between the two plates compressed and folded up to form the world's highest mountain ranges, which are the Himalayas and the Rockies. So your biggest, or like the Himalayas and Rockies. So your biggest mountain ranges in the world are caused by this motion. The friction from plate movement in the subduction zone makes the rocks melt, and this produces magma from which volcanoes are formed. What happens as a result of this action? The volcanic eruptions here are super violent a lot of times because of the relatively quick formation of the mountains of volcanoes and magma. The lava is shattered into many pieces by explosions and thrown as rocks, ash, and other debris. Tall, steep-sided cones are built up. So you can see the Osorno volcano in Chile over here, and you can see the steep sides. And earthquakes are frequent. The ground shakes from the force movement of rock against rock. All right. Another unique occurrence of a convergent boundary is, I put this in there a couple years ago after I went on a vacation over the summer to the Grand Tetons in Yellowstone. The United States doesn't really sit on a convergent plate boundary, except for like one little one. And that's what actually forms the Grand Teton Mountains. But they're all the way over in Wyoming, and you wouldn't expect there to be a mountain range in the middle of Wyoming of these tall, steep mountains. So the reason this is because that the subducting lithosphere plate ends up going more horizontal. It's a very small plate. So what you've got is you've got this plate, and instead of going down like we would normally expect, and here's the North American plate, so here's the North American plate, what happens is instead of that, it actually kind of just like flows underneath here and then starts going down. So where this friction happens, there's your Tetons. So it's kind of cool, little feature I wanted to bring into here that also forms all the cool, so all that friction also forms all the cool Yellowstone features like the geysers. So it creates what's called a hot spot, but it's formed by that friction of that one plate not being big enough and heavy enough to subduct all the way down, and so it takes some time. So all those features are pretty far inland, which is pretty cool. And please watch the video on that on your own time. All right, and finally, conservative and transform boundaries. Conservative and transform boundaries slide against each other. All right, they do not create nor destroy the crust. It conserves the crust that's in place. They may be moving in the same direction at different speeds or in opposite directions. What will happen is, and you can see here, these will create what's called a fault, and you'll end up getting these places where rocks kind of just sit there, and as it's moving across, they'll kind of catch, and then all of a sudden it will release. And when that release happens, that's when you get earthquakes. A lot of earthquakes in these areas, not as many as the consistently moving conservative boundaries. I mean, not conservative, subduction zone convergent boundaries, but still, you do get a lot of earthquakes here, and this is what you get fault, so like the San Andreas Fault in California. So this is what happens in California. Landslides, fires, and other destructive forces can be the result of earthquakes caused by conservative boundary shift. So basically what you have here is you have earthquakes that happen, and then lots of other things can happen because of the earthquakes, and we'll talk about that in the next chapter. You can see here, here's the conservative transform boundary. You got plates moving in opposite sides. You get these stress marks, and those can be where the earthquakes start. All right, and finally, hotspots. The last phenomena you need to know about are called hotspots. Hotspots aren't really the result of plate movement. They're not the result of plate movement in the most part. They can be at a plate boundary, near one, or far from one. They are theorized to be the result of extra hot mantle pockets that push their way to the surface. We already talked about Yellowstone, and that one is kind of the result of a plate movement. But Hawaii is not theorized to be as a result of plate movement. So what happens is that you have just like a random spot of hot magma that rises to the surface. And what that will do is that hot magma, because it's hot and it rises to the surface, it will push up and push the crust up, which will form mountains, actually volcanoes, because all of that lava is creating a lot of pressure that will make a lot of volcanoes. Now here's the cool part though. The plates that they're in, they're moving, right? So if you take a look at this, you took a look at the age in millions of years, right, of all these features, you can see that Kauai is a lot older, kind of like 4 million years older than Maui, right? So what happened? Well, Kauai and all these islands used to be all the way over here, all right? But what happened is that the plate, because it's moving this way, moved out of the hotspot zone. So this formed first, all right, when it was way over where Hawaii is now, and then Oahu, then Molokai, then Maui, and now the big island of Hawaii. Why is it the big island? Because it's the newest, and it stayed the longest, and these guys have had 1 million years or more to get covered with water on the other ends. So at some point, Hawaii, the big island, 1 million years in the future, will probably be smaller, and there'll be new islands formed. So you can see it's a continuous chain of islands, even though you can see it some are underground. It's just been continuously made as the plate moves that way. So that's what a hotspot is. All right, so that is it for 2.1.4. We're moving to 2.1.5 really quick because we're going to combine these two. All right, and this is evidence of plate tectonics. And this one, I really want you to look at paleomagnetism and watch this teacher, this professor, do a really good job of explaining the first type, which is paleomagnetism. All right, so there's other types of plate movement as well, or evidence of plate movement. So this is basically like, how do we know that this happened, this actually happened? So the key points to take home from the plate tectonic video, please make sure you pay attention to this, is that the first spot of evidence is called geologic fit. It is basically like if you look at a map of the Earth, you can see that it looks like pieces of a puzzle used to fit together. Now we know that as subduction zones, new crust is formed, or sorry, old crust is destroyed. At divergent boundaries, new crust is formed. So we know the land masses don't exactly fit together, but if you look at Africa and you look at South America, you can tell at one point those guys probably fit together like a piece of a puzzle. That's called geologic fit. That's probably the most obvious piece of evidence, but maybe the weakest in terms of like actually convincing somebody that this happened, because you're like, well, they look like they fit together. Well, okay, prove it. So we go on. So we know from looking at layers of rock that the magnetic poles on Earth switch every so often, and by every so often I mean hundreds of millions of years. All right. So the magnetic rocks on the crust change poles as you move away from known ridges. So if you look at a divergent boundary, all right, and you look at the sides of the divergent boundary, so this is the boundary, I'm going to call it B, all right, and if you look equidistant from here, see, the north and the south pole will shift every so often. So if you go and take a look at rocks on the sides of divergent boundaries, these two guys, all right, the rocks on this side and this side will have the same magnetic direction. At some point, they'll switch direction. And it just so happens that when that does happen, that happens at the same distance from the boundary that the other side does. And same thing here. So the magnetic poles, they switch places, which proves basically that here at this boundary, new crust is being formed and the plates are moving. And basically, when it's formed, it's going to have the magnetic properties of that time. So that's probably the most confusing one, but maybe the strongest piece of scientific evidence, right? There's evidence that the plates are moving away from each other there. So that's known as paleomagnetism. And then my final piece of evidence that my favorite is there have been bones of prehistoric creatures, namely the Mesosaurus, and plants found on and near South America and South Africa, suggesting strongly that at one point they were connected. So basically there will be places on Earth where dinosaur bones and other fossils, not just dinosaur bones, that's just my favorite, dinosaur bones and other fossils are found on separate continents that are separated by entire oceans now, right? Suggesting, and they'll be found nowhere else on the Earth. So they had to have been connected unless those animals swam across the entire ocean, which a lot of these animals, the skeletons, do not come back as amphibious or water type. So this evidence is known as paleontology or fossil evidence. So that's it for 2.1.4 and 2.1.5. It's a little bit longer one. We'll probably go over a little bit in class. Thank you.